welcome. Hey guys, welcome back. This might seem a little different to you since I'm not recording through a camera. I'm recording my monitor because today I'm going to teach you Python. Specifically, I'm going to teach you how to use the TensorFlow library, and we're going to create a handwritten digit recognizer with it. So as you can see, I've created two files here: handwritten digits classifier training and handwritten digits classifier usage. So first we want to import all of our dependencies. So we have to say import. We have to say import OS, then import CV2, import numpy as np, import matplotlib.pyplot as plt, and then lastly import TensorFlow as tf. So TensorFlow is what we're gonna make the model with. So firstly we say mnest is equal to tf.keras.datasets.mnest, and the mnest is like within the TensorFlow module. There's a data set for handwritten digit recognition, and it's called mnest. So tf.keras.datasets.mnest. Then we're gonna specify the training and the testing images or whatever. So we create a tuple. We say x train and y train, and then comma, we create another tuple x test comma y test is equal to mnest dot load data. So this is gonna load the data from the mnest, or basically the data set, and then it's gonna create these variables called x train, y train. Those are, so you can think of them if you want, like the x train is like the images and the y train is like the labels, and the x test is like the images for the testing, and the y train is the images for the labeling. It's the labels for the testing. Then we say x train is equal to tf dot keras dot utils dot normalize. So if you don't know what normalize means, so like the colors in a computer are like from 0 to 255, right? The amount of colors. So you can have like minimum would be 0, maximum would be 255. But that just makes it really complicated in a neural network. So what we do is we normalize those values. So the minimum would be 0 to 255. Now it's gonna be like 0 to 1. So that's what normalize does. So x train axis 1, axis equals 1. Then we do the exact same thing for x test. So I'm just gonna control D, x test, and then replace here x test. So we do the same thing for x test. Then we have to reshape the data input to add a channel dimension. So I don't really know what this means, but yeah. Xtrain, I can't find much info on this, is equal to xtrain dot reshape. So dot reshape -1, comma 28, comma 28, comma 1. And then we do the exact same thing again for the X test. Okay, I forgot to add an underscore. X test dot reshape X test. So after that's done, now you can skip this step if you want, but I usually do this in all of my AI models. So we're gonna apply augmentation to our data. So what that does, it like randomly shifts it randomly rotates the picture, it like increases or decreases the height, it zooms randomly, it does all that stuff. It does all that stuff. So it makes our model not overfit as easier, because we have a lot of data, and those data the data set is like kind of, what do you say, kind of augmented. So it's not just like pictures looking straight at you. Some are twisted, some are zoomed, some are have increased height, some have decreased height, decreased width, like that. So we're gonna say data gen is equal to tf dot keras dot pre-processing dot image dot image data generator. And then we're gonna pass in, so there are a lot of arguments you can pass into this, but we're only gonna pass in 4 for now. So I said rotation is equal to rotation range is, let's say, 10, and then width shift range is equal to, let's say, 0.1, and then let's just copy that, control D, but we're gonna make it height height shift range, it's gonna be the same thing. Then we're gonna say zoom range and that's also gonna be 0.1. So you can like play around with these values, you can do whatever you want. So now we're gonna do the model architecture. So we're basically, this is the AI kind of part of it. So we're gonna say model is equal to tf dot keras dot models dot sequential. And then so most people in here, they just specify a list of all the layers, but I don't really like to do that. So I just say model equals tf.keras.models.sequential, and then I close the brackets. I don't put anything in the brackets, and I say model dot add So we're adding a layer to the model. So model.add tf.keras.layers. First we want to make a flattened layer. First a flattened layer. And then the input shape is gonna be, it's gonna be 28 by 28 and 3. Now the 28 is, I think, the height, and 28, and this 28 is the width, and then 3 is the number of color channels, so like RGB, so 3 color channels, so we specify 3. But actually I forgot about this part. Our images are going to be black and white, so we don't need 3 color channels. And then we add another layer, model.add. Again, this part is like common in all of them, this tf.keras.layer, so you want to copy that. so this time we're gonna add a dense layer, and then it's gonna have 256 neurons. It's gonna have an activation. It's gonna have an activation function of ReLU, and then we're gonna say model dot add tf dot keras dot layers dot. This time we're gonna add a dropout layer. We're gonna add dropout layer with a dropout rate of 0.2. We're gonna dropout rate of 0.2. Then again model dot add, and then the same thing, tf dot keras dot layers, and then this time we're gonna add another dense layer. This is also gonna have 256 neurons. It's gonna have an activation of ReLU, and then model dot add tf dot keras dot layers, and we're gonna add another dropout layer, and with a dropout rate of 0.2 again. And then this is the last layer, model dot add tf dot keras dot layers, and then we're gonna add the last dense layer. So the amount of neurons of this dense layer depends on the amount of outputs we can have. So since we have, like, we can identify from 0 to 9. This data set only has from 0 to 9. So we can identify only from those two, from 0 to 9. Yeah, we can identify only from 0 to 9. So that means, like, in between 0 and 9 there are 10 different numbers. So we're gonna have 10 neurons. 10, and then the activation is, it's not ReLU, it's softmax. So now we're done with the model architecture. So we're gonna compile the model. Model dot compile, model dot compile, and then the optimizer is gonna be Adam. The loss is gonna be sparse, categorical, cross entropy. Cross entropy. Categorical. And then the metrics we want is just the accuracy. That's the only thing we want right now. And then we say history is equal to model dot fit. So basically we're training it right now. Data gen dot flow, not flow, and then we're gonna give it x train and then y train, and then the batch size is gonna be 8. Batch size is equal to 8. And then we're gonna have the epochs are gonna be 30. The validation data is gonna be x test and y test. And then we're gonna, this is just for actually we don't need the rest, so you just do that, and then we're gonna save the model. Okay, model dot save. You can save it to literally whatever you want. I'm just gonna save it as handwritten model. And then you're just gonna run this. For my computer it takes a lot of time to run this, so I already ran it before, so I'm gonna just pull that up. Don't mind everything here. So here it's right here, handwritten model. So you can see right here, handwritten model. I've run this before. So after you run that, got your handwritten digits classifier usage .py, and then again we're gonna import all of our dependencies. Import OS, import CV2, import numpy as np, and then import matplotlib.pyplot as plt, and then lastly import TensorFlow as tf. That's all our dependencies. So we're gonna say model is equal to tf dot keras dot models dot load model. So this is gonna load our model, so specify whatever you saved the model as. I saved it as handwritten model, and then we're gonna say image. Oh, by the way, for this you're gonna have to do this yourself. So you wanna go to paint you want to, let's say you want to go to paint, you want to resize the whole thing from whatever it is, you want to resize it to 28 by 28 pixels, and then you're just gonna draw any number in the pencil with the finest line you can draw. You're gonna draw any number, and then that's it. And then you have to save those in the directory. So I've saved them here. See, image1.png, image 2, 3. I've saved it up till 10. So we're gonna say image number is equal to 1. We're gonna say while os dot path dot is file, and then we're gonna give an f string, f digits, and one more thing. Yeah, we don't need digits. Yeah, don't write digits. Yeah, we don't need digits. So just be like, so actually, okay, this is for another project actually. Don't focus on this. Don't focus on this. That's for some other project. Okay, wait. Yeah, that's for another project. So those images are for something else. So you want to create a directory called digits, and then you want to save it in those. See, 1, 2, 3, 4 like that .png, and then we're gonna say digits, and then slash. We're gonna give image number, and then we're gonna give .png. Then we're gonna say square bracket, colon, comma, 0. Okay, no, we're gonna put a colon. We're gonna say try image is equal to cv2 dot im read f string digits slash image number dot png, and then we're going this is where we put the square brackets. So colon, comma, 0. Then what we want to do is we want to say image is equal to np dot invert. You gotta invert the image, because when cv2 reads it, it's gonna read as black. It's gonna read as white on black, but we trained our model on as black on white, so we gotta invert it. And then we're also gonna convert it to an np array, np dot array, and then we're gonna give image. Then we're gonna say prediction is equal to model dot predict model dot predict image. So basically what we're doing here is, in this data or digits, whatever, we have saved all these digits in order from 1 to 10. So we have to save them from 1 to 10, otherwise it just won't work. If we save them like image1.png, it just won't work. You have to specify that, or we can't just give them random names. So you have to give them the number, not the number name. And then we're basically all we're doing is we're going through each number or image in this digits directory, and we're just feeding them into the model, and it's trying to predict them. It's trying to predict them. And then what we're gonna do is we're gonna say print to the f string, printf this digit is probably a, and then in curly brackets we're going to say np.argmax, which basically takes the maximum value, and then prediction. It takes, so since our output layer here, it's here, our output layer has 10 neurons, so there are 10 different outputs. So it's just gonna take the max. So like say the first output has the max, like the first output has like a 1, and then the others have like a 0 on them. So the first is the max, so it's just gonna check which is the max. So it's just gonna check which is the max in prediction. Then it's gonna, then we just print that. Then we say plt dot imshow image, and then we give an index of 0, and then the cmap will be plt dot cm dot binary. And then plt dot show. That's not how you spell show. Yeah, plt dot show. Then except, like we put a try statement, we have to put an except in there. Except, just accept, just print error. Print error. Then we say finally we just increment image number by 1. So image number plus equals 1. So yeah, that's it, I'm pretty sure. And then if we just run this, it should work. So it takes some time, because when you import TensorFlow you have to import all this code, so it takes some time to import that. So just wait for it. And what is this? Has no attribute to model. Oh, it should be models. Okay, if I said model, just make it models. And just wait for it. So here's a 0 obviously, and it thinks it's a 0. It doesn't actually know what it is. This is like unfed data to it. It thinks it's a 0. It says this digit is probably a 0. Okay, that's correct. Then when you close that, it reopens the next digit. So this looks like a 1, and then it says this digit is probably a 1. So let's see, I don't know, I'll tell you how to calculate the loss or the accuracy. This is obviously a 2, and it says it's a 2. This is a 3, it says it's a 3. 4, it says it's a 4. 5, 5. 6, 6. 7, 7. 8, 8. 9, 9. So it got all of them correct. Like literally all of them are correct. So then what you can do is you can pull up the calculator. I'll tell you how to calculate the accuracy of your model based on whatever you fed it. So you just say the correct ones. So in this case, out of 10, all 10 were correct. So we say 10 and we say 10, and then since the total amount of images I gave it were 10, so we say 10 divided by 10. Wait, we say 10 divided by 10, and we get the answer as 1, and then we just have to multiply that by 100 times 100. So it's 100% accurate based on what I gave it. We don't know if I give it something else how accurate it will be. So based on what I gave it, it's 100% accurate. So it could be sometimes like 81% accurate, stuff like that. So that's it for today, and okay, bye.